I hope you have 15 minutes left on your clock because it's time for the final question. And of course, as always, number 6 is a series question. So let's begin. The Maclaurin series for natural log of 1 plus x is given by x minus x squared over 2 plus x cubed over 3 minus x fourth over 4. So alternating in sign, we are going from x squared, x cubed, x to the fourth. Bottom is increasing by 1, 2. And they are even giving us a general term of the Maclaurin series for natural log of 1 plus x. On its interval of convergence, this series converges to natural log of 1 plus x. Let f be the function defined by f of x is x times natural log of 1 plus x over 3. So instead of x, we're substituting in x over 3, and then we're multiplying the entire thing by x. Write the first four non-zero terms and the general term of the Maclaurin series for f. Well, let's think about this. We're plugging x over 3 into natural log of 1 plus x. We are replacing x with x over 3. So let's replace every single x with x over 3. So we are going to have x over 3 minus x squared over 3 squared times 2 plus x cubed over 3 cubed times 3 minus x to the fourth, 3 to the fourth times 4. And of course, we have to remember to multiply by x. So we have to multiply this entire thing by x, which should get us x squared over 3 minus x cubed over 3 squared times 2 plus x to the fourth over 3 cubed times 3 minus x to the fifth over 3 to the fourth times 4. And of course, you don't have to simplify the bottoms if you don't want to. You should still get 100% of the credit. Anyway, so we have found the first four non-zero terms. Now let's find the general term of the Maclaurin series. Well, they gave us the general term for natural log of 1 plus x, so let's utilize it. So we know we want to plug in x over 3 into x. So x over 3 to the nth power, divide by n, and we have to multiply everything by x. So we have negative 1 to the n plus 1, x to the nth power, and another x. So we have x to the n plus 1 power, divided by 3 to the nth power, divided by 3 to the nth power, and we have an extra n residing at the bottom. So this is the general term. This is the general term. So that's the answer to number 1. So let's go on to part B. Determine the interval of convergence for the Maclaurin series for f. Show the work that leads to your answer. Well, if you're trying to find interval of convergence, you start by finding the radius of convergence, and then you test if the series converges at the endpoint. So you check the radius first, then you are going to test the endpoint. Well, we have the general term, and we see lots of powers in it, so it's pretty obvious that the test to use is the ratio test, because when you apply the ratio test and you have powers in your expression, it usually simplifies very nicely. So let's use the ratio test. So we want to take the limit as n approaches infinity of the absolute value of the n plus first term over the nth term. So we have limit as n approaches infinity. Since you're taking absolute value, this negative 1 to the n plus 1 is going to go away. So we have x to the n plus 2, because now you have n plus 1. So a sub n plus 1. So you have n plus 1 or n plus 2 over 3 to the n plus 1 times n plus 1, all divided by a sub n, which we have. And of course, we don't have to worry about negative 1 to the n plus 1 because we are only looking at positive value. And what is this? That's limit as n approaches infinity, x to the n plus 2 over x to the n plus 1. Well, that's simply just x. And what else do you have? You have n plus 1 dividing at the bottom. And this dividing by n is going to flip back up. So it's going to go in the numerator. And you have 1 over 3 to the n plus first power, 1 over 3 to the n plus first power. And you have 3 to the nth power multiplied to it, and it should be in the numerator. And you know this is 1 over 3, so we have another 3 down below. And of course, you need the absolute value sign. And what is this? This thing is, let's go this way. Well, as n approaches infinity, the ratio n over n plus 1 is going to approach 1 because the difference between n and n plus 1 is going to become insignificant as n gets very, very large. So we simply have absolute value of x over 3 because n over n plus 1 is going to approach 1 as n approaches infinity. And by ratio test, you want this thing to be less than 1 or absolute value of x to be less than 3. So that's giving us that we know our series converges between -3 and 3 exclusive. Now we have to test the endpoints because they want us to give the interval of convergence, not the radius of convergence. The radius is 3, by the way. So now let's test the endpoint. So to test the endpoint, we want to test x value of -3 and x value of 3. When x value is -3, what happens to the general term? Well, we have -1 to the n plus 1 times -3 to the n plus 1 over 3 to the n times n, which is -1 to the n plus 1, -3, you can treat that as -1 times 3, each raised to n plus 1 power, over 3 to the n times n. Of course, we can make some simplifications. -1 to the n plus 1 times -1 to the n plus 1 is -1 to the 2n plus 2. And because 2n is even, that's multiple of 2, and you're adding 2 to that, you have -1 to the even power. So this entire thing is going to become +1. And you have 3 to the n plus 1 over 3 to the n, which is simply 3, and you're dividing by n. So the general term, when x is -3, becomes 3 over n. And we know the summation over 3 over n is going to diverge because harmonic series, the summation of 1 over n diverges. So we know it's going to diverge at x equals to -3. How about +3? When x is +3, we have -1 to the n plus 1 times 3 to the n plus 1 over 3 to the n times n, which is -1 to the n plus 1 times 3 over n. So we have 3 times the summation of -1 to the n plus 1 divided by n. And what is this? That's alternating harmonic series. Alternating harmonic series. And as you know, alternating harmonic series converges. It converges because the terms are decreasing in size. And we have alternating series, and terms are approaching 0. And term is approaching 0 as n approaches infinity. So we know this thing converges. So we know our series converges at x equals to 3. So that's telling us that our interval of convergence, we're not going to include -3, but we're going to include +3. So that's our answer for part B. Let's go on to the final part of the test. Are you guys not excited? Part C. Let P sub 4 of x to be the 4th degree Taylor polynomial for f about x equals to 0. And we actually know what that is because we already wrote down quite a bit of terms. And we're looking at P sub 4. We're looking at P sub 4 of x. So we're going to go all the way to the power x to the 4th. So this part is the P sub 4. So we know this thing is P sub 4. And we wish to use the alternating series error bound to find an upper bound for the absolute value of the difference between P sub 4 and f. So you're using P sub 4 of 2 to approximate f of 2, and you want to find the maximum value of the error. Well, you have alternating series. The series alternate in sign, so this is pretty easy to do. Because alternating series error bound states that the error is going to be less than or equal to the magnitude or the absolute value of the first term left out. In our case, the first term left out was the one with x to the 5th. And since we're looking at the absolute value, we only have to care about this part. So we have left out x to the fifth over 3 to the fourth times 4. So we're looking at x to the fifth over 3 to the fourth times 4, which is, so we know this thing is less than or equal to x to the fifth over 3 to the fourth times 4 when x is equal to 2. So we know our alternating series error is less than or equal to 2 to the fifth over 3 to the fourth times 4. And you can leave it as it is, or if you really want to, you can simplify it as 8 over 81. And we are done.